Hi everyone, my name is Nikhil Pimpalkhare. I'm a final year PhD student at Princeton, and I'm going to be presenting on some joint work with Zachary Kincaid, my advisor, and Thomas Reps on context-free reachability for almost-commuting transition systems. So the motivation of this work is to design new techniques for interprocedural program analysis. So program analysis is broadly about automatically computing properties of programs from their source code. And interprocedural means that the programs that we consider have function calls. So in this example, in the program on the left, it's got a recursive function call in its body. In this work, we consider a formalization of interprocedural programs which separates data and control. The way in which a program modifies data is modeled as a labeled transition system, and the way in which, and the control structure of the program is modeled as a context-free language. So on the right, we have the formalization of the program on the left. The control structure of the program is modeled by the context-free language generated by the grammar G. G generates a language by repeatedly replacing the start non-terminal S according to the production rules until you have a string of all terminals. So in the context of the program, the S non-terminal represents a run through the foo program. The A and B terminals correspond to the A and B operations in the program. And the production rules kind of identify the possible paths through the program. So either we just apply the A operation, or we do A operation, recursive call, then B operation. And the data manipulating semantics of this program are modeled as a labeled transition system, which is written here as two transition formulas. So the unprimed variables represent the pre-state, and the primed variables represent the post-state. So the transition corresponding to A says that X gets incremented by 1 and Y gets preserved, and the transition corresponding to B says that X gets preserved and Y gets incremented by 1. And these transition formulas model the state effect of the corresponding operations on the program side. And so we formalize the procedure on the left as the behavior of this labeled transition system along a context-free language of program paths. Our goal is to compute the reachability relation of this system, so the set of input-output state pairs that are connected by a sequence of transitions along a path in the context-free language. So the kind of abstract picture is here. We have a context-free language representing the program structure, and we have a labeled transition system representing the program semantics, and we want to compute the context-free reachability relation of the transition system. So this is the set of state pairs that are connected via the transitions along something in your language. I'll mention that sort of the key weakness of this formalization is that since it doesn't have access to unbounded memory, it can't model local variables, but it does provide a sort of mathematically clean way to answer research questions. And so in this work, we aim to answer the question, for what transition systems can we compute this context-free reachability relation? So this slide kind of recaps everything. So we understand interprocedural program analysis as computing this context-free reachability relation, and transition systems map each character in a finite alphabet of edges in your graph to some relation between input-output state pairs. And we want to compute this object, which is the set of state pairs that are connected by a sequence along the context-free language. So in order to answer this question, what transition systems are interprocedurally analyzable, we're first going to have to consider what theoretical tools we have to reason about context-free languages. So an important classical result is that we can compute the Parikh image of context-free languages. So the Parikh image of a word is a character count abstraction of it. So the Parikh image of this word identifies that there's 2 A's, 3 B's, and 1 C, but loses all information about the relative order in which these characters appear. And the Parikh image of a language is the set of Parikh images of the words within it. And so Parikh's theorem, which is a classical result from 1966, says that we can, it says that, and along with this other result from Verma et al. In 2005, say that we can compute a logical formula whose models define the Parikh image of a context-free language. And so what that looks like is when we have this is the grammar from the beginning, and this is the language that the grammar generates. So the Parikh image of this context-free language identifies that you're always going to have one more A character than B character, because every time you use the second production rule, you get one of each, and then your derivation is going to end when you use the first production rule, and that's going to give you one extra A. And so there is an efficient procedure for computing a logical formula like this one, which says that we're going to have a non-negative number of A's and B's, and we're going to have one more A than B. And we can use this formula in order to automatically compute the context-free reachability relation of programs in which all of the operations commute. So this is the program from the very beginning. This is the grammar that generates the paths through it, and the under bracketed part of the formula is the Parikh image formula from the previous slide. And since all of the operations in this program commute, we know that when we apply NA A operations and NB B operations in any order, we're going to have that X gets incremented by NA and Y gets incremented by NB. And so we're able to use the Parikh image in order to automatically compute this formula that's defining the context-free reachability relation of this program. This is the kind of image. So in order to get the reachability relation of this commutative transition system along paths through the context-free language, we can sort of factor through its Parikh image and use the universality of that object in order to compute the object that we want. I'll take a slide here to talk about what's happening sort of mathematically. So every transition system corresponds to a monoid. A monoid consists of a domain M, a composition operator that says how you take two things in your domain and combine them to get another thing in your domain, and an identity element. And transition systems can be sort of modeled inside of monoids, in which the monoid operator is relational composition, and the domain is the closure of the base transition relations under relational composition. And so the Parikh image is the universal commutative abstraction of languages. And so a key corollary of Parikh's theorem is that we can compute a logical formula representing the image of a context-free language under a homomorphism into a commutative monoid. And in the context of this transition system monoid that I defined at the top, what this means is that we can sort of use this recipe in order to compute the context-free reachability relation of commutative transition systems. All right, so that's all pretty cool, but a lot of programs are not commutative. So this program is not commutative. The x equals negative x plus 1 is not going to commute with the other operations. And so it's unclear that we can use the Parikh image in order to automatically compute the context-free reachability relation of this program. But we can via the contributions of this paper. So this paper extends the scope of context-free reachability to a rich new class of transition systems, which are these almost-commuting transition systems. And the way in which we compute the context-free reachability relation of these systems is that we compute an unfolded, bigger context-free language. We take the Parikh image of that language, and we use that object in order to compute the thing that we want. So what is a almost-commuting transition system? I'll start by example. So we identify a couple of different transitions which induce these almost-commuting transition systems. And zooming in on the top one, kind of the key property of these transitions is that they can factor into a transition from a finite set acted upon by a purely commutative component. And so this kind of decomposition is kind of the key thing that makes this operation almost commuting. These other classes, the decomposition is a little bit more complicated, but they also have decompositions in which they can all be turned into a transition from a finite set acted upon by a purely commutative component. So these are some examples of almost commuting transition systems. The way in which we formally define an almost commuting transition system is if the monoid that represents the transition system is an almost commuting monoid. So remember, each transition system corresponds to a monoid in which the composition operator is relational composition and the domain is the closure of the base transition relations. So a monoid is almost commuting if each element factors into one of finitely many monoid elements acted upon by a element of a commutative integer monoid. And additionally, the monoid operator meets this second kind of simple algebraic condition that's a little bit too technically subtle to discuss in this talk. And the key result of this paper is that we can compute a logical formula representing the image of a context-free language under a homomorphism into an almost commuting monoid. And like with the Parikh image, we're going to use this to compute the context-free reachability relation of almost commuting transition systems. I guess to repeat, the sort of recipe that we use in order to compute this reachability relation is that we unfold our context-free language into a bigger context-free language. We take its Parikh image, and then we use that in order to compute what we want. And I'm going to show you how this recipe works in the context of a program. So on the left is the non-commutative program that we saw before. That's actually an almost commuting transition system. And on the right is the result of doing this unfolding. So in the following slides, I'm going to try and convince you of two things. First of all, that this unfolding is equivalence preserving. So the input-output behavior of foo is equivalent to the input-output behavior of foo shell. And I'll also try to convince you that we can compute the input-output behavior of foo shell from its Parikh image. So let's start by trying to prove equivalence. We want to prove that the orange program is equivalent to the pink program. And I'm going to do this, try to be convincing just by showing a single example trace. So here's a trace through the orange program where we take the recursive case 5 times, and then we hit the base case. And there should be 4 more C operations, but I haven't diagrammed here because I'm only looking at what happens to the X variable. All right, so what I'm going to do is I'm going to multiply through the negations in each of these terms. Now, this trace through the orange program corresponds to this trace through the pink program. So foo even and foo odd describe the number of times that the X variable will be negated in the remainder of the trace. So the first operation in foo shell guesses whether there will be an even or odd number of negations throughout the trace. In this case, there is an odd number of negations, and so we're going to pick the 1 operation. And then the increments within foo even and foo odd are modified based on the context that they have about the remainder of the run. So for example, the B operation is incrementing X by 1, but the B0 operation is subtracting 1 because it has the additional context that the following foo odd call is going to perform an odd number of negations to the X variable, and we're going to end up with a decrement. So the trace through the pink program records increments in the final context in which they'll appear. So this means that at intermediate points throughout the trace, the pink program does not have the same x value as the orange program. But this is because the increments are happening in the context in which they'll appear at the very end. And so by the time we reach the end of the trace, both traces have computed the same x value. So in this way, every trace through the orange program corresponds to exactly one trace through the pink program. And foo is equivalent to foo shell. All right, and we can compute the input-output behavior of foo shell from its Parikh image. So this is a set representation of the Parikh image with this sort of operation order. So the top is the foo even case, in which we basically have an equal number of alternations between foo even and foo odd, ending in an A0 operation. And the second set is the odd case, in which we have one extra B1 operation, and then we have the even case, and then we have one extra C1 operation. And we can use this Parikh image in order to compute this sort of non-trivial procedure summary of foo shell, in which the first set corresponds to this first disjunct, and the second set corresponds to the second disjunct. The first disjunct says that x is not going to get negated. Y is going to increase by 2k because both C0 and C1 are incrementing y. And then the B0s and B1s will cancel out. And similarly, we end up with the second disjunct from the second set. And so we were able to automatically come up with the context-free reachability relation of this program from its Parikh image after we had unfolded it. So I'll hint that this unfolding is guided by the underlying structure of the almost-commuting transition system. So the finite set of transitions that are forming the decomposition, that's going to determine the size of the blow-up to get the other language. So what transition systems are interprocedurally analyzable? Almost-commuting transition systems. This paper identified a rich new class of transition systems for which we can compute the context-free reachability relation. We identified several examples of transitions generating almost-commuting transition systems, and we computed the context-free reachability relation of these systems by unfolding our context-free language and using its Parikh image. So this work can be viewed as a backend for an abstract interpretation-based program analysis. So a client would have to pick a suitable family of almost-commuting transition systems and develop an abstraction procedure. And then they could use our work as a sort of backend in order to automatically compute the reachability of that abstraction and end up with an overapproximation of the original program. And this work can also be viewed as an expansion of the applicability of Parikh's theorem to almost-commuting monoids. Thank you for listening.
All right, thanks. Are there any questions? Let's start here.
Several slides ago, you showed a rewriting of your original program into the almost commutative transition system. I wonder, like, if Daniel's choice is instead of non-deterministic, it's probabilistic. Is this kind of rewriting still possible? Like, would they still be equivalent? Or does this question even make sense?
I think that. So it really depends on. So you can replace this predicate, the even x, with different predicates, potentially probabilistic ones, but I would say it's like highly dependent on which particular predicate you put in to make sure that you still end up with the finite set.
Sounds good, thank you.
Okay.
On one of your earlier slides, you gave the kind of rules for your almost commuting transition systems, which essentially said your variables were over Z. So I wondered if you had like a multilinear version. So rather than just like these linear transitions you gave, could you use matrices, which don't often commute, but you might have similar rules? Or is it something to do? Yeah, so you were on the slide just then.
Was it this one?
No, there's like the one with more text.
Oh.
There we go.
Sorry, this one.
Yes.
Okay, yeah.
So you have a commutative integer monoid. So I wonder whether you've got this kind of system over a Z. Could it be over Z to the D, say, or whether there's any...
It can be over Z to the D. I guess I wrote it as an integer monoid here for simplicity's sake, but really the property that we care about is that it's finitely generated.
Wonderful.
Thanks. The examples that you gave us on the slides are, of course, very small, like academic examples, but I'm sure you have some kind of more practical things in mind when you develop this theory, probably some examples of things that you would like to analyze, right?
Yeah, so this sort of actually, sorry, this top class of transitions, I guess one of my prior works at UPSLA in 2024 designs kind of a practical abstract interpretation-based technique, which uses this in order to compute resource costs and to model different aspects of programs. So there are practical use cases for this.
Okay, thanks. Maybe one last question while the next speaker sets up. Okay. So maybe I could ask a question while the last speaker sets up. So you had these, you use context-free languages to model these traces, but of course you're over-approximating. Mm-hmm. Do you think there's a generalization to something context-sensitive where you could do the analysis by looking, for example, at the condition statement?
I think it's possible that you could apply additional formulas. You could refine the Parikh image formula in order to be more context-sensitive. But off the top of my head, I don't know of work that compute such formulas. Yeah.
Thanks. Yeah, thanks again for the talk.